On the next slide, I use Laplace transform. I will ask you, what do you remember? What do you know or what you don't know about Laplace transform?
Laplace transforms for solving differential equations in circuits with using like capacitors and inductors and stuff like that.
Laplace transform makes the calculations for finding the charge and currents and changes in those in the time domain, whereas in the time domain you'd have to do integrals and derivations. The little transform makes it easier so that those are done as multiplication and division.
Laplace transform is a technique that was presented by Laplace, a French mathematician, in the 1800s. Electricity was just starting to be understood by that time. So people could not even think or imagine that Laplace transforms would be useful. By the turn of the century, 20th century, so just imagine 1905, 1908, pretty much the beginning of the modern age of electricity. And people did not use Laplace transforms by that time. Another technique that was very useful before Laplace, it was by Heaviside, Olivier Heaviside. He used another technique that was called operational calculus. And from 1900 until 1925, 1930 was the way that people were trying to use to solve circuits. And then there was a book that happened in 1930s by Carlson, where he revisited everything that was proposed by Laplace more than 100 years before. And then he said, you know, these circuits here, you can use Laplace transforms. By the same time, complex numbers were proposed to solve circuits in steady state. So it took about 20 or 30 more years, 1950s and 1960s, until all of these were kind of organized in a way that became a strong foundation in electrical engineering. So when we talk about Laplace transforms today, people just assume immediately that's a technique to solve circuits. But it's not true. There is a history on that. There is something that happened. We are less than 100 years, because Laplace transforms, they were proposed in 1930. So 90 years ago, somebody was proposing this for the first time. It's kind of recent, in the history, I would say. In the lecture today, I'm going to show you how to use a Laplace transform for a simple circuit. And it's already a little bit complicated, but I'll try to detail a bit how to use it, because I want to emphasize that, yes, given a circuit, you can take the Laplace transform and you can make it algebraically. You can do multiplications and divisions. You do algebra, because when you take second derivative of x plus whatever coefficient multiplied by the first derivative of x. So you have a differential equation that becomes rather complicated to solve. When you learn in math, I did also, you learn how to solve the first order differential equation. You learn how to solve the second order differential equation. And then your math professor is going to talk about the third order, fifth order. Nobody knows how to solve them. They have to use some very esoteric techniques to solve. The engineers, they just take the Laplace transform. And then you have algebra. You manipulate the S, is a S domain. And then you come up with a solution. And if everything is fine, you go back to a table that you reverse your Laplace domain into time domain. Sometimes you do not even need to do the reverse, because you can use a Laplace transform for simulation. I teach another class, a course where I emphasize Fourier for steady state and Laplace for transient analysis, and we do all the computer simulations using this. Fourier becomes a fast Fourier transform, and Laplace becomes a block diagram. I'm kind of diverting a little bit here, just to show you what you could do in your future. I'm go back now to the lecture. I will present how to use Laplace transform for a few slides. But my next few DC-DC converters, I'm not going to use Laplace transforms. I'm going to solve in an approximated way. You're going to see how. But today I'm using the full technique.